Today we're going to talk about PCA as a way to decrease dimensionality for the input data for artificial neural networks. And we'll start from the results which show what advantage can give us this type of dimensionality reduction. For example, here we see training of the full-scale shallow artificial network for 60 by 60 pixel images for German traffic size without any reduction in dimensionality, and you can see here, but barely, about 14 minutes to train 5 classes of data of this GPU. If we take a look at another example where we reduced number of dimensions tenfold, so just 10% of the original images, it took 7 minutes, so and about the same accuracy. So basically we saved half of the time and resources and get about the same accuracy, though we discarded 90% information and left just 10 useful stuff. And before we go into detail and code how we will do this, let's go a little bit back to basics of vector spaces. So when we work with images, we have a set of images, and we represent them as a product of pixel channels. So for example, if we have n pixels, this is product of n integers, integer channels. And if we want to convert this set into space, we basically set with defined structure or operations. Vector space, this is summation and multiplication. So we have our set and these operators which are transformations into the same space. And vector space, we can spawn it using basis vectors. So this minimal number of vectors which linear combinations of summation and multiplication by a field of real numbers can give us any vector inside the space. So any vector can be represented as linear combination of one basis. And when we write vector in this nice column form, we write here multiplicators of the basis vectors. For example, this representation, the real one, from this way. So we represent A, B, and C in respect of this basis vector. But exactly same vector could be represented through another basis, for example, this U with W, and it will be completely different multiplicators, but again, we can represent the same vector like here. And what we also can define, what we can do with linear spaces, actually the fun part is transformation from one linear space to another. So we can say that transformation T gets object from space A to space B. And if transformation is linear, which is also keeps through these linear combinations, this transformation could be conveniently represented as matrix. So what we do in a lot of machine learning stuff, these multiplications vectors and matrices. Matrix, we multiply by this vector and we get another vector, which means this is either another vector in the same space or another space. How we can and want to interpret it. There is also nice eigenvector decomposition. We probably come back to it later when we start talking about PCA, but basically idea is that generic, very complicated, messy transformation which represented to full-scale matrix. For some vectors we can find few vectors which will be conveniently given same result as multiplication by scalar. So these vectors are called eigenvectors and these values are eigenvalues. Basically this is basis for eigenspace in which our transformation will look very nice. So this diagonal matrix with everything at the top and bottom 0. So this really simple, clean transformation. And when we convert any vector of the basis space into this eigenbasis, we can again easily do all these transformations using the eigenbasis. And here's a little bit how we can change basis. So, for example, if we have vector x in basis ing something, for example, Cartesian coordinates, and we somehow magically got these eigenvectors v and w, which represent again our Cartesian ones. How we can convert? We just simply like from eigenspace to our space, we multiply vector to eigenvectors, and from our space to eigenspace. This is inverse of eigenvectors multiplied by our space x and get eigenspace representation. And now we return back to related topic. So when we have number of observations of our images represented as columns or rows, we can calculate covariance matrix, which is composed from again nice diagonal, which is summation of difference between mean and our current point squared, and actual variances and covariances of two respective dimensions. How we can interpret this covariance matrix could be done different ways, but we can, for example, see this diagonal like, for example, we see this cloud observations, and we have delta y squared. It could be seen as some kind of rubber band or spring which wants to move our axis to this particular observation, and we can have these rubber springs attached to every point, and there will be some kind of equilibrium. And covariance, we can see, we can have some kind of analogy from mechanics as a lever. So we have lever and we have force, so we have weight moment. And when we multiply, for example, if we want for some reason multiply our vector by covariance matrix, means we're doing some kind of transformation to another space. And if our covariant matrix is interpreted as mechanical space as forces and rotating moments, what could be the space? Something related to acceleration or velocity. But anyway, if we try to find eigenvectors and eigenvalues for covariance matrix, the resulting eigenvalues or this diagonal eigenmatrix will look like a matrix with zero rotating moments. So this is something like rotation equilibrium. So as you can see in many videos, you have this axis x and y, and not really convenient cloud of points, and then we rotate this axis and we come to some kind of equilibrium which creates a maximal variance on one axis and minimal to another, which is like really convenient for discrimination power. So if we have some axis with really high variance, we can try to use any type of categorization technique to separate one type of observations from another. And we have, we can have another dimensions in which we don't have much of the variance. So basically, any observation will give about the same number. So this dimension would be really useless for categorization, and we can just discard it. And again, as we previously saw with this eigen vectors matrix, we can convert all our observations from our space, this particular application space of the images, into eigenspace with minimal rotational moments, and take a look for each dimension what kind of variance we get. Just retain rows of observations with high variance, it means with high discrimination power, and discard everything which will go below particular threshold. And when we work with Matlab, let's go to actual code. We do exactly what we just discussed. So in the code which reads files which attach to this dataset, we just read the file, and then we actually reshape it to standard size. In this particular implementation, this is 60 by 60 pixels, and all three channels are flattened, so we have just one big row. And then we go in this loop and collect all possible files, and also we collect separate array for labels for this class. When we're done with this, we can start doing this PCI stuff. We can use standard Matlab PCA function, but it does a lot of unnecessary stuff, so it's easier just go with eigenvalue covariance. So to get this matrix of all observations, we calculate covariance matrix, then we get eigenvectors, matrix of eigenvectors, and we use previously shown formulas to convert all our observations from our image space into eigenspace. So right here, so is our original one, and here we have rotated into eigenspace. We can also calculate for each dimension what kind of variances we have, and just separate ones with really high values. So we have the bagger here, and for example, if we take a look what we have results from standard PCA, what yeah, so we see these variances just decrease. So this is decreased order. And in case of our variances, we have just a row representation, this is smaller ones and bigger ones. Just show you few parameters and switch between them. So we see this is same number. So we're calculating same thing. But we don't have overhead from this PCI unnecessary stuff. And then we can, yes, so we prepare just simple shallow network with sequence of leg. This version, just this one works. This one, which would be more convenient for some reason, implemented, but sequence of leg is fine. Then we have fully connected layer, then softmax, and because the softmax we have classification layer with cross entropy, which goes nice with softmax. Otherwise, if you use standard sumo squared error, we have local minimum maximum tabs. So these training options using standard gradient descent with momentum, with memory basically, batch size, then rate, epochs. And here what we do, we just select few dimensions we want to train our network against and just train. And when we want to categorize particular vector, we do exactly the same. So we have this test images read into memory, then we reshape them to standard 60 by 60, flatten to one size array vector, and collect data we want. Then we again having eigenvector matrix convert from our space of images into eigenspace, and the resulting data we just supply again and cut unnecessary dimensions, supply into predict function, and get results which test image is which. So yes, you can play with these files, play with number of principal components, may create less shallow network. I comment because it takes really longer, so you can add one more or two more layers, but it takes a lot of time to train deeper networks. So enjoy and experiment what you